This meeting is being recorded.
So this next problem from chapter 8, problem 31, gives us some examples of reagents that can be used to perform a syn dihydroxylation. So we're going to be adding two hydroxide groups in a syn fashion across the double bond. So we have in our first set of reagents here, we have osmium tetroxide as a catalyst, and then we have NMO. So again, if you see these pair of reagents, we're going to have a syn addition across our double bond. So our product would look something like this. So they made us note here that we want to pay special attention to the number of chiral centers being formed. So we have 2, so we'll have this product plus enantiomer. In our second reaction here, we have in step 1 osmium tetroxide again, and then we have addition of aqueous sodium bisulfite in the second step. So this can also accomplish, right, these set of reagents, another set, can accomplish this syn dihydroxylation. So we have our double bond. Over here will not create a chiral center because there's 2 other hydrogens, 2 of the same group, but here we would create a chiral center and we would note that with a wedge. So we have that plus the enantiomer as our products. With molecule C, again, we're going to add 2 hydroxide groups across a double bond with cold potassium permanganate in basic conditions with sodium hydroxide here. These are our third set of reagents that accomplish the addition here. So again, we're going to have syn dihydroxylation, so both will be from the same face, both hydroxide groups. So we could draw both on a wedge or both on dashes. So that plus the enantiomer as our product. Actually, this would be, I apologize, a meso compound, right? If we look at this and this reflective symmetry here, if we determine these 2 chiral centers to be symmetric, they actually will be achiral. So for problem C, we only end up with one product, not an enantiomer. So let's take a look at D here. So again, we have the same reagents. So we know that we're going to have dihydroxylation across our syn, across our double bond, right? So they're syn addition here. So we create no chiral centers here. So here's where my double bond was. So I add OH over here, and that's not a chiral center, nor is the other side of the double bond where I add my other OH. So no stereochemistry consideration here. And in our last molecule, E, we see another set of reagents. So we have osmium tetroxide listed as our catalyst, but we also use this co-oxidant, this tert-butyl hydroperoxide, so we can use less of this more toxic type of substance here, this osmium tetroxide. So this is our last set of reagents that will accomplish this transformation, this dihydroxylation. So at this point here, we would create a chiral center. So we put our OH group on a wedge, and then the other end of the double bond would not be chiral. So we end up with this product plus the enantiomer for molecule E when that has dihydroxylation in a syn fashion.